Can you truly destroy an enemy you cannot even reach, no matter how many millions of dollars you spend trying? Deep in the rugged highlands south of Isfahan, a dark, silent mountain became the ultimate testing ground for this terrifying question, enduring weeks of relentless bombardment from the most advanced bunker-busting weapons on Earth, only to defy the world's greatest superpower in a way that left military planners utterly speechless. Ifu. You want to join an exclusive circle of critical thinkers who look beyond the surface of global conflicts to uncover the hidden truths of modern warfare. Take a single second right now to hit that subscribe button, turn on all notifications, drop a like on this video, and share it with a friend who loves deep dive military strategy. To truly understand the mystery of the missile mountains south of Isfahan, we have to start on the ground, looking up at the peaks through the eyes of the people who live in the valleys below. For several weeks, the residents of Isfahan witnessed a nightly spectacle that seemed to belong to a science fiction movie rather than modern reality. Night after night, the horizon would light up with a sudden, brilliant flash, followed seconds later by a low, rolling rumble that shook the glass in their windows and vibrated deep within their chests. The skies above the mountain hummed with the invisible, ghostly presence of the world's most sophisticated aircraft, flying at extreme altitudes to deliver a payload of unmatched destructive power. From the safety of their homes, the locals watched as smoke and pulverized rock billowed into the night air under the cold glow of the moon. It was a picture of absolute, overwhelming force. Anyone watching would have assumed that nothing could possibly survive such a ferocious, concentrated onslaught. Yet every single morning, as the sun began to rise over the ancient city, the dust would settle, the steel doors on the side of the mountain would slide open, and massive ballistic missiles would climb majestically into the sky, launching from the exact same mountain that had just been battered hours before. It was a pattern that repeated itself day after day, week after week, leaving onlookers and intelligence analysts alike in a state of profound disbelief. This was not a story about a secret base that Iran had managed to keep hidden from the watchful eyes of Western intelligence satellites. Everyone knew exactly where it was. The coordinates of this subterranean fortress were well known to military planners in Washington and Tel Aviv. It was a primary target, marked for complete destruction, and hit repeatedly with some of the most specialized, expensive, and powerful conventional weapons ever designed by human hands. Yet, despite the billions of dollars in technology and the sheer volume of explosives dropped on its peaks, the facility never stopped working. It was a sobering, humbling reality that forced a complete reevaluation of what is actually possible in the realm of deep earth warfare. To find out how this mountain achieved such an impossible feat of survival, we have to look back at the history of how Iran built its underground empire in the first place. This was not an overnight project. The origins of Iran's deep strike defenses date back to the brutal lessons of the Iran-Iraq War in the 1980s. During that conflict, Iranian cities were repeatedly pounded by Iraqi Scud missiles, and Iran's air force, cut off from Western spare parts after the revolution, struggled to defend the nation's airspace. The Iranian leadership realized they could never match their adversaries in a conventional air-to-air dogfight. They simply did not have the industrial base to build or maintain a modern fleet of fighter jets. Their solution was as brilliant as it was desperate. They decided to build an air force in reverse. Instead of building planes to drop bombs, they would build an immense arsenal of ballistic missiles to strike their enemies from afar. And to protect this priceless arsenal from being destroyed on the ground by superior Western air forces, they decided to hide it deep within the earth itself. Over the course of 3 decades, Iran transformed its mountainous terrain into an absolute fortress. They did not just dig simple trenches or concrete basements. They hired international engineering consultants, acquired heavy tunnel boring machines through front companies, and mobilized thousands of specialized construction workers to hollow out the roots of their mountain ranges. They chose their locations with extreme care, focusing on areas where the geology itself provided the ultimate shield. The Zagros mountain range, which stretches across the western and southern parts of the country, became the primary canvas for this massive engineering effort. These mountains are not made of soft dirt or unstable sandstone. They are composed of some of the densest, hardest metamorphic and igneous rock formations on the planet. By carving their missile facilities deep into these ancient geological structures, Iranian engineers were not just building bunkers. They were co-opting the natural strength of the planet itself to act as their armor. This brings us to the specific target of the campaign, a massive peak known as Sof Mountain, situated just to the south of the strategic city of Isfahan. This location was not chosen by accident. Isfahan is the historical and technological heart of Iran's military-industrial complex. It is surrounded by nuclear research facilities, missile assembly plants, and major military airfields. Sof Mountain served as the heavily fortified crown jewel of this defensive network, housing a massive subterranean city that stored, assembled, and prepared ballistic missiles for rapid launch. The mountain itself is a geological marvel. It is made primarily of dense granite bedrock, a material with a natural compressive strength that boggles the mind. To understand the scale of what we are dealing with, consider the concrete used to build modern skyscrapers and highways. This high-strength concrete is designed to withstand a compressive pressure of around 5,000 to 10,000 pounds per square inch. The granite bedrock of Sof Mountain, however, has a compressive strength measured between 25,000 and 40,000 pounds per square inch. It is a material so hard, so unyielding, that even the most advanced steel-tipped drills wear down to useless nubs within hours of trying to cut through it. This was the natural shield that stood between the mountain's internal chambers and the outside world. To the planners in the Pentagon, Sof Mountain represented the ultimate challenge. It was a target that could not be silenced with standard GPS-guided bombs or conventional cruise missiles. To even stand a chance of damaging this facility, the United States had to bring forth the absolute heaviest, most destructive non-nuclear weapon in its entire inventory. That weapon is the legendary GBU-57 Massive Ordnance Penetrator, commonly known as the MOP. The MOP is not just a bomb. It is a 30,000-pound monster of engineering, designed with one single, highly specific purpose: to punch through solid rock and reinforce concrete to destroy targets buried deep underground. The sheer scale of the GBU-57 is difficult to comprehend. It is over 20 feet long and more than 2 feet in diameter. It is so incredibly heavy that no standard fighter jet or conventional bomber can carry it. The only operational aircraft in the entire United States military capable of carrying and deploying the MOP is the B-2 Spirit stealth bomber. Each B-2 can carry 2 of these massive weapons in its internal bomb bays, flying them silently across oceans to deliver a blow of unparalleled force. The design of the GBU-57 is a masterclass in metallurgy and physics. The outer casing of the bomb is not made of standard steel, which would simply shatter upon hitting solid rock at high speeds. Instead, it is forged from a highly classified ultra-dense steel alloy containing nickel, chromium, and molybdenum. This alloy is treated to be both incredibly hard and remarkably tough, allowing the bomb to withstand the astronomical forces of impact without breaking apart. The nose cone of the weapon is specially shaped to act as a kinetic wedge, concentrating the entire 15-ton weight of the bomb onto a tiny surface area as it strikes the ground. When the MOP is dropped from high altitude, it accelerates under the force of gravity, reaching near supersonic speeds before it makes contact with the target. It does not explode on impact. If it did, the blast energy would simply blow back into the open air, leaving the underground tunnels completely untouched. Instead, the bomb relies on its immense kinetic energy to physically push its way deep into the earth. It uses a highly sophisticated smart delay fuse that counts the number of voids or concrete layers it passes through, waiting until it has reached its absolute maximum depth before detonating its high explosive warhead. It is a weapon that represents the absolute pinnacle of human engineering, costing several $1 million per unit to manufacture. Yet, when this unstoppable force of human technology met the immovable object of Sof Mountain, the results did not go according to the plans drawn up in the sterile briefing rooms of Washington. Before we explore the fascinating physics of why these massive bunker-busting bombs failed to collapse the tunnels, and the incredible, calculated gamble made by military commanders behind the scenes, I want to invite you to join our growing community of history and military enthusiasts. Take a quick second right now to tap that subscribe button, hit the notification bell, and leave a comment below sharing your thoughts on this incredible technological duel. Your active support is the primary engine that allows us to produce these deep-dive, high-quality investigations week after week. To understand why the world's most powerful conventional bomb could not silence the missile mountain, we have to look at the harsh, unyielding mathematics of rock mechanics. When a weapon like the GBU-57 strikes a mountain of dense granite, a fascinating but highly limiting physical interaction begins. As the nose cone of the bomb collides with the bedrock, the sheer force of the impact generates a localized pressure wave of millions of pounds per square inch. This pressure instantly pulverizes the rock directly in front of the bomb, turning the solid granite into a fine, highly compressed powder. The shape of the bomb body then forces this powdered rock outward into the surrounding bedrock, creating a narrow, self-sealing channel through which the rest of the 30,000-pound steel dart can slide. However, this process of pulverizing rock consumes an unbelievable amount of kinetic energy. The friction between the ultra-hard steel casing and the surrounding granite is so intense that it generates temperatures hot enough to melt metal. This friction acts as a massive brake, rapidly slowing the bomb down as it travels through the earth. Even with 15 tons of weight and near supersonic impact velocity, the GBU-57 has a mathematically defined physical limit to how deep it can go before its forward momentum is completely spent. In solid, unbroken granite of the highest density, that limit is estimated by geophysicists to be somewhere between 20 and 30 feet. No matter how much specialized steel you pack into the casing, or how aerodynamically perfect you make the nose cone, the laws of physics simply do not allow a conventional kinetic penetrator to go any deeper into solid rock. Now, compare that 20 to 30 foot penetration limit with the actual layout of Iran's deep missile cities. According to detailed Western intelligence reports and geological surveys, the critical infrastructure of these underground complexes, the storage rooms, the command posts, the fuel depots, and the launch crews, sits at depths of up to 500 feet below the surface of the mountain. In some extreme cases, these tunnels are buried under 1,600 feet of solid rock. This massive gap between the maximum reach of the bomb and the actual ceiling of the underground facility is what geologists and military engineers call the dead zone. The dead zone is a vast expanse of solid granite hundreds of feet thick that acts as a perfect natural cushion against explosive energy. When the GBU-57 reaches its maximum depth of 30 feet and detonates its massive explosive charge, the blast wave does not travel downward to crush the tunnels. Instead, the energy behaves like any physical force. It follows the path of least resistance. Since the hundreds of feet of solid granite below the bomb are incredibly dense and unyielding, the explosive energy rushes upward, blowing out through the entry channel and creating a spectacular crater on the surface of the mountain. The shockwave that does travel downward through the bedrock is rapidly absorbed and dissipated. As the wave moves through the crystalline structure of the granite, the microscopic bonds between the quartz and feldspar crystals absorb the kinetic energy, converting the destructive shockwave into harmless seismic waves. By the time this seismic tremor travels through several hundred feet of rock to reach the ceiling of the missile tunnel, it has lost almost all of its destructive power. To the soldiers and engineers inside the mountain, the detonation of a 30,000-pound bunker buster 500 feet above them does not feel like a world-ending event. It feels like a minor, distant tremor. They might see a light fixture flicker or hear a faint low rumble like thunder in the distance, but the structural integrity of their steel-reinforced concrete tunnels remains completely undisturbed. This physical reality created a profound and frustrating dilemma for American and Israeli military planners. If you cannot physically reach the interior of the mountain to destroy the missiles and the launch crews, how do you defeat the facility? This is where the concept of functional defeat comes into play. If you cannot destroy the target itself, you try to destroy its ability to interact with the outside world. In the case of a subterranean missile city, the weak points are not the deeply buried tunnels, but the surface portals, the massive concrete and steel doors where the missiles must emerge to be launched. These portals are where the solid granite mountain meets the open air, and they are highly vulnerable to precision strikes. The strategy developed by Western commanders was to use layered attack profiles. They would deploy a combination of stealth bombers, standoff cruise missiles, and precision smart bombs to repeatedly strike the entrances of the facility. The goal was to collapse the rock face directly over the portal doors, burying the massive steel launch tracks under thousands of tons of heavy rubble. By doing this, they hoped to trap the transporter erector launcher vehicles, known as TELs, deep inside the mountain where they would become permanently useless, unable to fire their deadly payloads. It was a highly sophisticated, logical approach that utilized almost every major precision weapon in the American arsenal, all focused on a single geological target. But as the campaign progressed, a new, even more complex set of challenges began to emerge. Challenges that had less to do with the physics of rock and more to do with the cold, hard realities of global military logistics. The United States is undoubtedly the wealthiest and most technologically advanced military power in human history, but even its vast resources are not infinite. One of the most closely guarded secrets of modern military strategy is the surprisingly small size of the global stockpiles of specialized, high-tech weapons. The GBU-57 Massive Ordnance Penetrator is not a mass-produced weapon like the standard 500-pound dumb bombs carried by fighter jets. Each MOP is practically hand-built by specialized defense contractors, requiring months of precise manufacturing, quality testing, and specialized metallurgical processing. Because of this, the total inventory of GBU-57 bombs in the entire United States arsenal is estimated to be extremely small, likely numbering in the dozens rather than the hundreds or thousands. When you are engaged in a sustained high-intensity conflict, the rate at which you consume these precious weapons can quickly outpace your ability to replace them. This scarcity created an incredibly difficult strategic calculation for American commanders during the strikes on the Isfahan missile mountain. If you expend your entire national stockpile of 30,000-pound bunker busters on a single mountain in Iran, what happens if another crisis erupts on the other side of the world? What if a conflict breaks out in the Pacific, where China has spent decades building its own massive networks of deeply buried military command centers and underground submarine pens? What if a crisis occurs on the Korean Peninsula, where North Korea's leadership is hidden deep inside some of the most heavily fortified mountain bunkers on Earth? To empty your quiver of deep penetration weapons on one target would be a strategic blunder of the highest order, leaving the nation dangerously exposed to aggression from other global adversaries. This strategic anxiety was further compounded by the staggering depletion of other long-range precision weapons during the broader conflict. According to detailed defense reports, the United States and its allies fired roughly 1,100 long-range stealth cruise missiles during the wider campaign. This represented a massive, historic expenditure, consuming a huge percentage of the entire remaining stock of that specific class of weapon. When military planners looked at the rapidly dwindling numbers in their global ammunition depots, they realized they could not afford to keep throwing their most advanced, expensive weapons into a seemingly bottomless geological sinkhole. They had to make a hard, calculated decision to preserve their remaining high-tech reserves for potential future conflicts with near-peer adversaries. This logistical reality, more than any failure of technology, was the driving force behind the tactical shift on the ground. Instead of attempting to completely obliterate the deeply buried missile cities, a task that would have required a sustained, months-long bombardment using almost every heavy penetrator in existence, commanders chose to focus on the much more limited goal of sealing the entrance portals. It was a compromise born of necessity, a clear demonstration of how resource scarcity can dictate the limits of military power in the modern era. If this deep, analytical look into the hidden physical limits of modern warfare is completely changing the way you view military conflicts and the true limits of technological power, please take a quick moment to share this video with someone who loves science, engineering, or global history. Your personal shares are the absolute best way to help our independent, deeply researched content break through the noise of the YouTube algorithm, and don't forget to hit that thumbs up button to show your support. But even the strategy of sealing the entrance portals proved to be far more difficult and temporary than military planners had hoped. The problem with sealing an entrance is that rubble can be cleared and concrete can be repoured. This is where the concept of the repair loop becomes critical to understanding the ultimate outcome of the campaign. Once the heavy bombardment of the Isfahan missile mountain began to slow down, and particularly when temporary ceasefires or pauses in the fighting took hold, the dynamic on the ground shifted instantly from destruction to reconstruction. The Iranian military had spent decades preparing for exactly this scenario. They did not just build underground launch pads. They built a highly organized, deeply integrated civil defense and engineering infrastructure designed to survive under the most extreme conditions. The moment the sound of the departing stealth bombers faded into the distance, the mountain would come alive with activity. From hidden secondary exits and underground equipment bays that had escaped damage, massive engineering crews would emerge into the open air. These were not ordinary construction workers. They were highly trained military. Engineers, equipped with heavy earth-moving machinery, armored bulldozers, rapid-setting concrete mixers, and specialized diamond-tipped rock-clearing drills. Working under the cover of smoke screens and local air defenses, these crews worked around the clock with a level of speed and efficiency that stunned Western intelligence observers. They cleared the collapsed rock from the launch tracks, patched the damaged concrete portals with high-strength steel-reinforced materials, and restored power to the massive blast doors. Within hours of a strike that satellite imagery had marked as a highly successful entombment, the facility was once again fully operational, ready to slide back its steel doors and launch another wave of ballistic missiles into the morning sky. This remarkable resilience highlighted a fundamental truth of modern military engineering. The speed of reconstruction can often match, or even exceed, the speed of destruction, especially when the target is protected by a mountain of solid granite. To permanently keep the portals sealed, the attacking forces would have had to maintain a constant 24-hour aerial presence over the mountain, striking the repair crews the moment they emerged to clear the rubble. But maintaining such a continuous, high-risk air campaign over highly defended airspace was a virtual impossibility. It would have required a massive commitment of aircraft, tankers, and electronic warfare platforms, exposing them to continuous risk from ground-based air defenses and consuming immense amounts of fuel and maintenance hours. In the end, the sheer physical mass of the mountain gave the defenders a decisive advantage in the battle of endurance, allowing them to absorb the heaviest blows and rebuild their outward-facing infrastructure faster than the attackers could afford to destroy it. However, it would be a mistake to assume that Iran's subterranean missile cities are completely invulnerable fortresses. While they are remarkably safe from the external blast energy of conventional bunker busters, they carry a deep, highly dangerous structural vulnerability on the inside. an Achilles heel that has been closely analyzed by Western security experts. When you build a massive military base deep underground, you are forced to make a series of profound engineering trade-offs. The most significant of these trade-offs is the problem of space and confinement. In a standard surface-level military base, different facilities are spread out over miles of open ground. The fuel depots are far away from the barracks, the ammunition dumps are isolated in secure sectors, and the launch pads are placed at safe distances to prevent an accident in one area from destroying the entire base. In an underground missile city, however, everything is crowded together inside a highly confined, interconnected network of tunnels. Because of the immense cost and difficulty of boring through solid granite, space is at an absolute premium. Every foot of tunnel must be used to its maximum capacity. Satellite imagery and leaked blueprints of these facilities have revealed a deeply worrying design philosophy. Unlike highly sophisticated Soviet-era or Western nuclear bunkers, which are built with extensive compartmentalization, many of Iran's tunnel networks lack proper blast-resistant partitions or heavy isolation doors, separating different sections of the facility. Missiles are often stored nose to tail in long, continuous corridors. Even more alarming is the handling of rocket fuel. Many of Iran's older ballistic missiles, like the Shahab-3, rely on highly volatile, corrosive liquid propellants. Now, this fuel must be pumped into the missiles shortly before launch, a delicate and highly dangerous process that often takes place in the very same tunnels where soldiers live, sleep, and work. This lack of compartmentalization creates a terrifying risk of a catastrophic chain reaction. If a single high-precision weapon, perhaps a smaller, highly maneuverable bunker buster like the GBU-57, manages to find its way through a ventilation shaft, a secondary entrance, or a temporarily open portal door and detonates inside the tunnel network, the physical consequences would be absolutely devastating. In an open-air explosion, the blast wave and the heat dissipate rapidly in all directions. But inside a narrow, concrete-lined tunnel, the explosive energy has nowhere to expand. The tunnel acts exactly like the barrel of a giant shotgun, channeling the blast wave, the extreme heat, and the toxic gases down the entire length of the corridor with concentrated, terrifying force. This blast wave would instantly rupture the thin metal casings of nearby missiles, releasing highly flammable liquid rocket fuel into the white-hot air. The resulting inferno would trigger a series of secondary explosions, detonating warheads, igniting fuel reserves, and turning the entire subterranean complex into a raging furnace. The toxic, suffocating gases generated by the burning propellant would be sucked through the ventilation system, overcoming the life support filters and suffocating the launch crews long before they could reach the surface. It is a sobering reality that reveals the double-edged sword of deep underground warfare. The very same granite mountain that protects you from the outside world can instantly become a massive, inescapable concrete tomb if the enemy manages to punch just one single precise hole through your outer defenses. To see this contrast in action, we only have to look at what happened during the campaign against Fordo, Iran's highly fortified nuclear enrichment facility. Fordo is built deep inside another granite mountain range, constructed with a level of security and depth very similar to the Isfahan missile mountain. Yet, when the GBU-57 Massive Ordnance Penetrator was deployed against Fordo, the operational outcome was remarkably different, achieving what independent nuclear analysts concluded was a highly significant, meaningful setback to Iran's uranium enrichment program. Why did the bunker-busting campaign succeed at Fordo when it had failed to silence the missile mountain? The answer comes down to the extreme difference in the sensitivity of the technologies housed inside these two facilities. A ballistic missile is a highly rugged, incredibly durable piece of heavy military hardware. It is designed to withstand the immense vibrations, G-forces, and extreme temperatures of supersonic rocket-propelled flight. It can be bumped, shaken, and exposed to significant physical shocks without sustaining any damage to its internal guidance systems or solid fuel motors. The technology used to enrich uranium, however, is the exact opposite. The heart of a nuclear enrichment facility consists of thousands of highly sensitive, rapidly spinning gas centrifuges. These centrifuges rotate at astronomical speeds, often more than 1,000 revolutions per second, to separate uranium, isotopes. At these extreme speeds, the centrifuges operate on the absolute edge of physical tolerance. They are balanced with microscopic precision, relying on magnetic bearings and perfect alignment to keep from tearing themselves apart. Even the tiniest physical disturbance, a microscopic wobble or minor vibration traveling through the granite bedrock, can cause the rapidly spinning rotors of the centrifuges to touch the outer casing. When this happens, the result is a catastrophic self-reinforcing failure. The wobbly centrifuge instantly disintegrates, throwing metal shrapnel into neighboring machines and triggering a chain reaction that can destroy entire banks of centrifuges within seconds. This explains why the GBU-57 was so incredibly effective against Fordo despite the immense depth of the facility. The U.S. bombers did not need to physically penetrate the ceiling of the centrifuge halls to stop the enrichment process. They only needed to strike the top of the mountain with enough force to send a massive, high-frequency shock wave traveling through the granite bedrock. When this seismic energy reached the centrifuge halls, the vibration shook the delicate machines just enough to disrupt their balance, causing thousands of them to instantly self-destruct in a cloud of twisted metal. It was a brilliant, highly successful demonstration of how a weapon can achieve a strategic victory through indirect physical effects. But this strategy was completely useless against the rugged, heavy steel ballistic missiles housed inside the Isfahan mountain. The missiles did not care about vibrations. The shockwaves that destroyed the delicate centrifuges at Fordo simply washed over the robust missile launchers at Isfahan, leaving them completely unharmed and ready to fire. As military planners in the Pentagon and across the globe continue to study the humbling lessons of the Isfahan mountain campaign, they are actively reshaping the entire future of deep strike warfare. It has become painfully clear that the current generation of conventional bunker busters has reached the absolute limit of what is physically possible using standard kinetic penetration and chemical explosives. You simply cannot build a conventional bomb heavy enough or fast enough to punch through 500 feet of solid granite. To break this geological deadlock, military engineers are now exploring highly advanced next-generation concepts that sound like they belong in the realm of science fiction. One of the most promising avenues of research is the development of hypersonic kinetic energy weapons. These weapons do not rely on chemical explosives at all to destroy their targets. Instead, they are designed to travel at extreme hypersonic speeds, more than 5 times the speed of sound, using the sheer, unimaginable force of impact to generate a blast of thermal and kinetic energy that can pulverize rock at depths never before thought possible. By hitting the mountain with such astronomical speed, these weapons would generate a shockwave so intense that it could physically collapse the deep tunnel structures through sheer seismic force, bypassing the need to physically drill through the rock face. Other engineers are exploring the use of advanced robotic drilling systems and high-powered lasers deployed from stealth platforms, designed to quietly burn through the granite bedrock over time to create a direct path for smaller, highly precise explosive charges. But until these exotic technologies become a practical reality on the battlefield, the ancient, silent granite of the mountains remains the ultimate winner of the physics battle. The story of what really happened inside Iran's missile mountain after the strikes is not a simple story of technology failing or of a superpower lacking the will to win. It is a profound, deeply humbling lesson in the enduring power of the natural world. It is a reminder that despite all of our high-tech sensors, our stealth bombers, and our multi-million-dollar GPS-guided munitions, some of the most formidable fortresses on Earth are still those built by nature itself. When the sheer, unyielding mass of an ancient mountain collides directly with the absolute pinnacle of human engineering, the mountain does not care about the cost, the technology, or the political will of the nations fighting on its surface. It simply absorbs the blow, turns the destructive energy into a harmless vibration, and stands silent and unbowed, waiting for the dust to settle so the struggle can begin anew. This is the real, sobering story hiding beneath the peaks of Isfahan, a story of physics, resource scarcity, and geological depth that will continue to shape the strategic calculations of global empires for generations to come.